All right, students, here we go again. Chapter 6, okay? Circular motion, orbits, and gravity. All right. Wrong PowerPoint. Okay, students, here we go again. Uniform circular motion is what we're going to be on today. Now, as you can see, we've already discussed centripetal acceleration. Remember, it's center-seeking acceleration. And you say, well, how can we have acceleration if the velocity value is not changing? Okay, now it can be moving in a circle, but let's just say we gave it a velocity of 10 meters per second. All right, well, that's constant velocity, is it not, Mr. Shields? No, because the direction is constantly changing. Okay, and that's what I'm trying to show you there. Okay, so just because the value, the magnitude may be constant, does not mean that there's not acceleration. Because remember, what is velocity or acceleration? Acceleration is changing velocity. Okay, the velocity is changing. If the direction's changing, the velocity is changing. Okay, and of course we know the units are meters per second squared. Okay. Now again, this is one of those you need to write on your formula card. Centripetal acceleration for uniform circular motion. Write all this down, write the units down. Center-seeking motion. All right, now, if we have a ball at the end of the string, the ball is accelerating because we just said the direction is constantly changing. Now, all right, I've already done a little scribbling here. I want to delete this if I can. There we go. Because it's kind of a little bit cluttered. There we go. And I'll probably have to do this on a couple other slides. Sorry about that. All right, now when we look at frequency, period, frequency, and speed, how do we define the period? The period of an object in motion, now whether it's circular or whether it's like a pendulum, periodic, doesn't matter. If it's moving, all right, the period is the time it takes to make one complete revolution, or we could say one cycle. Okay, one cycle, the time it takes to complete one cycle. So we define that as the period, T, and that's capital T, okay, capital T. And of course the units are what? The units for period is seconds, okay? Okay, now, if we take period and say, all right, now I want to know how many revolutions or how many cycles occur every second, that is called frequency, okay? We call that frequency. And the units for that is called the reciprocal seconds, but it's actually the SI unit is called the Hertz, named after Heinrich Hertz, who invented radar, okay? And we abbreviate that HC, like that, okay? Heinrich Hertz. Now, but you can write it that way too, okay? And you'll hear me say reciprocal seconds. All right, now, so how do we find the velocity of an object moving in circular motion? Well, if you remember that how we find, and I'm on page 162, how we find the velocity of linear motion, remember that's delta x over delta t. Well, there's your period in seconds. What about this right here? That is angular displacement. Angular displacement, okay? So angular displacement is actually in radians, okay? It's in radians. Now, I know they put an R there. But here it's still in meters, but I'm fixing to show you something where it's in radians. Okay, now, so this is equal to that. And you say, why is that the case? If you remember how to find the circumference of a circle, that's why. Okay? All right, now, so let's take and substitute for period, because if we remember, frequency is 1 over t, and we substitute for t right there, look what we get. We get 2 pi f. Now, for whatever reason, they didn't go over this in the text with you, or either I'm just blind as a bat, but I have not seen it. 2 pi f is actually called omega, or that is called angular frequency. An angular frequency, the symbol for angular frequency is the lowercase Greek letter omega. It looks kind of like a W. And the units, what is the units for angular frequency? It is radians per second. Okay? Radians per second. So we can write this equation, V is equal to omega R. All right? And it simplifies it for us, doesn't it? So, again, what is omega? Omega is 2 pi times the frequency, or omega is what? Substitute for frequency. 2 pi over what? The period, right? So there's two different ways we can write angular frequency, okay? So you need to put that on your formula card also, okay? Because it is actually moving in an arc, and an arc is an angle. So we get what is called angular frequency from that, all right? Now, if we go on and take centripetal acceleration and then start substituting, see, look, we can even substitute angular frequency here. We could put that here if we wanted to for V. See, they substitute for V here. You square it. So we could actually substitute that there. All right, and it would become, we can find the acceleration, the angular acceleration, okay? Angular acceleration is a little different, though, than linear acceleration, all right? So don't confuse the two. So, but if we just go back and we substitute, and I'm going to erase all this. I hope you've written it down. If we go back and substitute these equations in here, we substitute this equation right there, and then this equation right there. Notice we get two different equations. All it is substitution to find centripetal center-seeking acceleration. Now here they give an example to find out what is the maximum rate. When a CD is spinning at a maximum rate, how much time is required for one revolution. So we know period. We want to know how fast it's moving and what is this acceleration. Well, notice we had to take 540 revolutions per minute and convert it to revolutions per second. And so we have to do what? Divide by 60 to get rid of the minutes, and we get 9 reciprocal seconds, or 9 hertz. So then we take that and substitute it into our period equation, and we get 0.11 seconds. We continue on, and we can either substitute period with that other equation, or frequency. They chose frequency. It's a little easier. Don't have to divide. And notice we get an velocity of 3.4 meters per second. Okay. Then substitute again into your acceleration equation, and notice what we get. 190 meters per second squared. Man, that is moving on. Have you ever noticed how fast the CD is spinning when you open it? Okay. All right. And then, of course, that's just explaining the process there. All right. Now, let's look at dynamic motion. Okay. If you look at going around in a circle, circular motion, if you've ever thought about, now we understand centripetal acceleration, well, if we've ever thought about the amount of force produced, because remember, if an object's accelerating, then it should be creating a force, right? Because Newton's second law says that when an object is accelerated, or it will accelerate in the direction of the applied force. So we get what is called centripetal force, and that is mv squared over r. And you say, well, now where in the world did you get that? Well, if you go back and you substitute right here, okay, if you substitute for acceleration, centripetal acceleration, right here, if you go back and substitute centripetal acceleration, that's how we get that equation, okay? Remember, centripetal acceleration, and it should have a C there, v squared over r. Well, okay, substitute it right there. And we get mv squared over r, okay? And so this is called centripetal force. Okay, centripetal force. So that's the equation. And of course we know the units because it's a force. The units are the Newton, which is a kilogram meter per second squared. Okay. All right, now, so you've got a particle moving in a centripetal, or you've got a particle or an object moving in a circle. The centripetal force will always be center-seeking because, remember, Newton's second law says F is equal to ma. The force and acceleration are directly proportional to one another. So notice if the acceleration is in the center, then the force is towards the center, okay? All right, now, if we have a ball at the end of a string and it's being swung in a horizontal circle, what force is producing the centripetal acceleration of the ball? Well, think about it. It would have to be the tension in the string. Okay. All right, think about it. You got a ball going in a circle, and it's going around. The tension, all right, it's going to cause a force. Got a ball at the end of the string being swung in a horizontal circle. What is the direction of the net force on the ball? Well, it has to be towards the center of the circle. Okay, all right. Forces in circular motion. All right. Notice if you've ever been in a car or riding a bicycle or on a motorcycle, when you hit a curve, you feel your body, you feel like your body's going to go, out the door. Your body hits the door. Like right here, you're going to hit the door. You say, well, why do I get that feeling? Well, it's because of inertia, okay? Now notice they say a centrifugal force will never appear on a free body diagram and never be included in Newton's laws. Well, I know you hear people say centrifugal force, but it's actually due to inertia, okay? And inertia is the tendency of an object to resist change in motion, which is basically the same thing as Newton's first law, okay? It's really the same thing. So, we don't say centrifugal force, we say you hit the door because of inertia. Why? Because your body wants to keep going in a straight line. So you were moving along here in this direction, then all of a sudden you hit the curve. Well, the car is going to the left, but your body wants to keep going straight. Okay? And that's why you feel that sensation. All right? Now, when we look at apparent weight, now there's a difference in apparent weight and actual weight. If you've ever been on a roller coaster and gone through a loop, you've noticed when you're at the top of the loop, you feel much lighter. You're at the bottom of the loop, you feel much heavier. Well, it's all a matter of forces. All right. Notice when you're at the top, remember center seeking. Now you say, well, I'm not hooked to anything. It doesn't matter. You're going in a circle. Centrifugal force is always going to be towards the center of that loop, no matter where you are. And so your normal force is in this direction. So your normal force is here. Your weight is in this direction. Weight is here. We got weight, we got F normal. So notice they're all moving in the same direction, so therefore you're going to have less weight. You're going to weigh less. You're not going to actually, your apparent weight will be less, okay? All right. However, when you hit the bottom of the circle, notice that center seeking, centripetal force, your normal force, but your weight is in the opposite direction. So you're going to weigh more. Your apparent weight will be more, okay, not your actual weight, okay? And this is just explaining what I just explained, okay? All right. So this is how we would write it mathematically. And remember, force is a weight, or weight is a force, Weight is a force. And so look what happens. All right, we do some substitution. And this is equation for a passenger at the bottom of a circle. All right. So that would be weight apparent. And of course, the units are newtons, y'all. But if you're at the top of the circle, your apparent weight, notice it, the formula changes. This is for the top of the circle. The other is for the bottom of the circle. Okay? Notice you have to subtract out your weight. All right? Excuse me, at the top of the circle, yeah. So you weigh less. Your apparent weight is less. Okay? All right, and there it is. Right there, boom. Okay? What about the speed? All right, what we call the critical speed. The speed for which the normal force is 0, we call that the critical speed. All right? In other words, the normal force and your weight cancel each other. Well, we take, and notice this is centripetal velocity, we call that, or excuse me, not centripetal, critical speed. Sorry about that. Notice we substitute, we take our equation, and we solve for what? We solve for velocity. All right? In other words, where again, it's got to be where the normal is 0. Okay? In other words, your normal and your weight cancel each other out. All right? Now, notice they tell you that this is the slowest speed at which the car can complete the circle, or the, if you're on the roller coaster car, or any circle, okay? So here's another equation, critical speed, and of course the units are meters per second because it's velocity, okay? All right, circular weights and weightlessness. All right, and orbital motion. Now, when you have an object moving around another object, let's say a moon moving around a planet, we call these closed trajectories, or orbits, okay? And an orbiting projectile is in free fall. Now, what does that mean? That means its apparent weight is 0. In other words, it appears to have a 0 weight, even though it doesn't, okay? It's in free fall. Now, we talked about that, I think, in chapter 5 video. Okay? So, when we look at orbital motion, we want to look at acceleration. Notice that the force of gravity is a force that causes, of course, centripetal acceleration of an orbiting object. Now, how did they get that? Well, look, if you take your equation for acceleration, Newton's second law, we substitute force right here, we substitute mg. Look what happens. When we substitute weight in its place, the m's cancel out, and we wind up with g. So centripetal acceleration is equal to the force of gravity and vice versa. All right. Now, with an object moving in a circular radius, this is a centripetal acceleration, or it will have, if you take the orbit, it's the same thing. Notice if you substitute, you're still going to get g. Okay? If you substitute your equation for velocity there, you're still going to get g. It all cancels out and you're going to get g. Okay? Now, if the object moves parallel to the surface with a speed, then the speed of the orbit is this right here. The square root of the gravity times the radius. Okay? All right, so make sure you write these equations down. This is an object moving parallel to the surface. In other words, you got surface here and it's moving parallel to it. Okay? All right. All right? So make sure you write this equation down. So if we have an orbital speed of a projectile just skimming the surface of a smooth, airless Earth, what is its orbital speed going to be? All right, notice that it is, and notice they take the radius of the planet. Notice it is very high, 7,900 meters per second. Are you kidding me? Okay. So that would be the orbital speed of a object going around the Earth. Now, that's an airless Earth, okay? Notice that's 18,000 miles per hour. So what is this telling us? This is telling us that an object in orbit around the Earth it has to have an orbital velocity of 18,000 miles per hour to stay in orbit. If it falls below that, then guess what? It crashes to the Earth, okay? So when they have all those objects up there in orbit around the Earth, they have to maintain at least 18,000 miles per hour or it will fall back to the Earth, okay? That's what that means, okay? Now, if you want to calculate the period of a satellite, and that's what you need to label this, period of a satellite, okay, then again we take and substitute, or we just take our equation where we found velocity a little earlier and solve for period. And notice what it becomes. It becomes 2 pi times the square root of r over g. Okay? All right? So write that equation down, period of a satellite. There you go. Right there. And of course that unit is seconds. That's the units. It's period. That looks like fun, don't it? Okay. Astronauts on the International Space Station are weightless because, why? They're in free fall, y'all. Okay? They are in free fall. All right, the moon, of course, like all satellites, is simply falling around the Earth. All right? So we could find the period of the moon. And notice we get about 11 hours instead of 1 month. This is because the magnitude of the force of gravity and thus the size of G decreases with decreasing distance from the Earth. All right? And we're going to look at that here in a little bit. Called the inverse square law. All right, now, when you take two objects and they are rotating around or revolving around, one's revolving around the other, well, one thing that Newton discovered is that we have a constant in our universe. It's called universal gravity. Okay? And no matter where we are in the universe, planets will obey the universal law of gravitation. We haven't found anything to violate that, even though they are beginning to really question it. Astrophysicists are. Okay, and this is what he proposed. He said the force is inversely proportional to the square of the distance between the objects. That is called the inverse square law. In other words, the force is equal to 1 over r squared. Now, do the masses come into play? Sure they do. All right? Sure they do. And it's directly proportional to the product of the two masses. Okay? All right, now remember, we're talking about celestial objects. So, the force of 1 on 2 is equal to the force of 2 on 1. Y'all, that right there is Newton's third law, isn't it? It sure is. They obey Newton's third law. They have to. So we come up with this equation, and we label it capital G. It's called the universal, or it's called the gravitational force, is equal to capital G m1 times m2 over r squared. And capital G, the value for capital G, well, I'm sorry, doggone it. and I don't remember it right off the top of my head because I haven't worked with it in a while, is, and this is on page 175, 6.67, so G, this constant, and you need to write this on your formula card, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared, okay? And you need to write that down, and that's the gravitational constant. Okay? That's what capital G is. All right, so let's look at some situations. The force of planet Y on X is what? The same. Newton's third law, okay? Don't forget. All right, do not forget that. Newton's third law. All right, the gravitational force between these two asteroids is 1,000,000 newtons. What will the force be if the distance between the asteroids is doubled? All right, force is equal to 1 over r squared, inverse square law. If you double the distance, what's 2 squared? Well, 1/4, isn't it? So it should be that right there, right? And it is. Inverse square law, okay? All right, if you travel to another planet, what would the force on the moon be? All right, we can find the weight. This is actually your weight on the moon. And you say, well, where did they get that? Well, we did some substitution. If you'll notice right here, we take F is equal to MA and W is equal to MG. And we substitute in, and notice what we get. Substitute it into his law of gravitation. So if we want to find the weight on the moon, we take the mass of the moon times the mass of the earth and then square the radius of the moon, not the earth, the radius of the moon. Now likewise, if we want to find G, well, look, we take mg, put it right there. Notice that the masses cancel out. And this goes for any planet. And then we can find the gravitational constant. In other words, the force of gravity, acceleration of gravity on any planet. There's your equation. There's another equation to add to your cheat sheet. Okay? So the weight on the moon is the same as his gravitational force equation, except we're just using moon now, moon and earth and moon. All right, and you would do the same if you want to know what would your weight be on Jupiter. You would use Jupiter right here, okay, and then Earth, and then so on and so on, okay? Now, notice this right here. This is G for a planet. This is the gravity for any planet equation. So make sure you write that on your formula card, okay? All right, if we use these values for the mass and the radius of the moon, we compute what? The gravity on the moon, and if you want to write that down, you can, is 1.62 meters per second squared, okay? All right, now, notice if you have a 70-kilogram astronaut wearing an 80-kilogram spacesuit would weigh more than 3 on 30 on the Earth, notice that it drops to 54. It's basically 1/6. The gravity of the moon is 1/6 Earth's gravity. Weigh 120 on the moon, you weigh 120 on Earth, you weigh 20 on the moon. Okay? All right, Planet X has free fall acceleration at the surface. Planet Y has twice the mass and twice the radius. All right. On planet Y, what would the G be? All right, so Y has 2 times the mass and 2 times R. What would G be? Well, let's go back and look at our equation. So it is G is equal to what? Capital G, M of what? y over r squared. So now we got 2m, but we got what? 2r squared. So that becomes what? 2m over what? 4 or 1/2. So what is half of 8? 4. Okay. See how I did that? All right, you got a 60-kilogram person stands on each of the following planets. On which planet is his or her weight the greatest? All right. F is equal to G, M of planet times M. Whoa, excuse me. It's a little m, lowercase. Over what? R squared. Okay, which one has the smallest radius? That one does. This is small, that means this is big. So it has to be A. All right. Gravity and orbits. All right. Newton's second law, of course, we know that the centripetal force is going to be equal to what? Well, again, we're doing some substitution here. We've already found that the force on the moon is this, right? Well, remember, force, Newton's second law, is ma. And centripetal force is still going to be mv squared over r. Not going to change. So if we want to find the speed of a satellite in circular orbit of radius about a star or a planet of mass m, this is how we would find it. Right here. Again, going back and solving for v, setting this equation equal to that equation, and solving for v, right? And notice it becomes the square root of g times the mass, okay, divided by r. So you need to write that on your formula card. We've got a lot of formulas, don't we? And that's what you need to label it right there. And of course the velocity, the units, come on y'all, that's not going to change. You should know by now when you see velocity, it's meters per second. Okay. All right. What about the period? Well, again, we do some substitution. And we get this equation right here. Period squared is equal to what? So it's the relationship between the orbital period and the radius, r, for a satellite in a circular orbit around the object of mass m. So notice the equation becomes t squared. Now look, you would want to simplify that and say t is equal to the square root of 4 pi squared over gm r cubed. Okay. Okay. Two satellites have circular orbits with the same radius. Which has a higher speed? Well, duh. Neither. They have the same radius, so the planets have the same radius, so look, they're not going to change, y'all. Notice it is proportional to the radius. Have y'all been seeing that? Look at this equation. Radius. Look. Radius. Do you see that? All right. Two satellites have circular orbits with the same, all right, we've already been over that. Two identical satellites have different circular orbits. Which has a higher speed? All right, well, what do you think? Have you ever looked at a bicycle tire as it's rolling, as you're moving down the street? You watch somebody riding a bike. You always notice it's faster towards the center. The one with a smaller orbit, y'all. Okay. And that's it. And I hope this has helped.